We'll just get started. So thanks for being here. My name is Jonas Mueller, and I'm one of the co-founders and chief scientists at Cleanlab. And our vision is really to build algorithms and software that help you systematically improve data sets using machine learning, using automation, rather than doing all this work manually. And so there's a lot of hype around data-centric AI, this term coined by Andrew Ng. And the idea is really that rather than focusing on modeling, which has been sort of the main theme of the past 10 years of machine learning, you can also focus on the data and just improving the data and get improvements in your downstream applications without actually changing anything about your models. And really, 80% of most machine learning and AI developers' time nowadays is spent in this data prep phase, and there's just a big need for algorithms and software to help make it more streamlined. And as we all probably know, data is just as important as what kind of model you're using. I think there's a good quote that you are what you eat applies a lot more to AI systems than to most humans. And yeah, we really see that. And top organizations like OpenAI, this slide's maybe a little outdated now that we're on to DALL-E 3, but they really realize this, they realize the value of this. They have huge teams of people that are just poring over the data. And for example, here, they really went through this big data set for training DALL-E 2, which is this image, text-to-image model, and really handled all kinds of issues like nearly duplicated images, images that were low information, labeling errors where the text didn't match the images. And it's sort of obvious, right? Like if you're training such a model with text that says like a car, but the image is a plane, then the model might generate some crappy things when you try and create a car. But the problem really is like finding these kinds of issues and dealing with them at scale without being OpenAI and having a huge team of people that you can hire. And other organizations like Tesla, Google, they realize this, and they're spending the same amount of effort really to just curate these data sets relentlessly and build essentially what are the top machine learning models that are deployed today. And to make this more concrete, let's just focus on one kind of data issue that's really common in real world data, which is just mislabeled data or label errors. For example, in these famous machine learning benchmark data sets, like MNIST and ImageNet, you just have data points that are straight up incorrectly labeled because of human annotated errors. And so actually where we got our start in this space was we had done some research on algorithms to identify this mislabeled data and ran these algorithms just on all the most famous data sets in machine learning that were, these are being used by thousands of researchers to prototype their algorithms, and getting 1% performance increase with like a new model is a big deal on these data sets. And we just ran our software on all of these data sets and found that tons of the data was mislabeled, and this had just not really been talked about or realized in the community. And so it attracted like a lot of attention and a lot of press. And really, the thing to emphasize is that these are like very highly curated data sets, and in most companies, enterprises, the quality of the data is much worse than these data sets studied by thousands of folks. And it just shows the need for algorithms and automation to discover such issues. You're not going to find these sort of things just manually looking at data commonly. And so when we're talking about data-centric AI, just to sort of lay out my perspective, because this can mean a lot of things to many people. Some people think like, so what, this is just machine learning. Like it's just not good old-fashioned AI, but data-focused AI. But really what we're thinking about here is a different approach to doing machine learning in general. So in traditional machine learning, like the data scientist thinks they have to manually do all the exploratory data analysis, do all the work to discover the data issues, fix them before they start training their machine learning models. And then once they go into, say, machine learning mode and they finish their data prep, they kind of just dive straight into improving the model using all the tricks that you've been taught in your machine learning courses over many years, like changing the loss functions, regularizations, different neural network architectures, etc. But actually, this initial machine learning model that you've trained on your data set already knows a lot about your data. It has captured a lot of the information in your data, and you can actually use this model to discover issues and actually improve the data using algorithms in an automated and systematic way. And so what you can do is I'll cover some algorithms in this talk that consume as inputs essentially the machine learning model, whether it be its representations or predictions for your data. These algorithms can then map that to different kinds of problems that have been detected in your data, which you can then resolve to produce a better version of your data set. After that, you can of course go back to modeling mode and just try hard to produce the best machine learning model you can. But really what makes data-centric AI, in my opinion, is the fact that you can just retrain your initial machine learning model on that better version of the data without changing any of your modeling code and just get better results already. And you can iterate this in a virtuous cycle that at some companies this is being called a data engine. But really this idea of improving the model, improving the data, and just iterating those two steps. And at Cleanlab, what we built actually many years ago while we were still grad students at MIT was this library that I had mentioned that allowed us to discover all these mislabeled data points in the most famous machine learning data sets called Cleanlab. And this is just an open source library that essentially has a collection of algorithms in it that will consume any machine learning model inputs that you have and help you find problems in your data set. And that makes this library really general. It works for all kinds of data modalities because it's never actually touching the raw data. It's only interfacing through your machine learning model that you've already trained. And it works with pretty much any kind of standard machine learning model and really just consumes essentially the information learned by this model. So that could be the feature representations like embeddings of your data, as well as probabilistic predictions about your data from the trained model. And so this is really like all the code you need to discover a bunch of issues in a data set. It's really easy once you've trained your machine learning model to just run this and quickly see a laundry list of different kinds of problems in your data. And just some examples, say for a computer vision data set, say a cat-dog classification data set to keep things simple, might include like nearly duplicated data, mislabeled data, outliers, which are just abnormal data, often indicating problems with your data sources, non-independent data points. When you think your whole data set is actually independent data, there might be drift or statistical interactions between data points. All of this also works for text data, as I mentioned, and many other data modalities. And so, for like customer service chats, we can discover mislabeled intents. Also ambiguous data where, even if I have 50 people go annotate certain data points, they may not agree, and that might indicate that you should either redefine your annotation instructions, you should bring in more experts to resolve such cases, but unlike the label error, say, maybe it's just not a good idea just to have somebody else look at it again one more time. And really the key thing that we emphasize throughout all of this is simplicity. So, for those of you who have been in data science for a long time, in statistics, data mining, machine learning, there's thousands of papers out there, thousands of pretty complicated algorithms for outlier detection, all kinds of drift detection, things like that. But really what we've been realizing over time is just once you have like a pretty good machine learning model, you can just use really simple algorithms and run those with a good machine learning model and really do far better than these really sophisticated techniques. Maybe at any one point in time, some of these more sophisticated algorithms can outperform things today, but machine learning is just constantly improving. The models are always improving. The training sets that these models are being trained on are constantly growing. And just running the simple algorithm, because the algorithm is simple, it's compatible with future versions of machine learning models, whereas oftentimes the more sophisticated type of methods, they're specific to one kind of machine learning model because they require changing something about its training procedure, changing something about the architecture itself, and that makes them no longer applicable once better and better machine learning models come out. But for example here, for detecting outliers, literally we just measure the distance to the k nearest neighbors, like in the embedding space of a trained neural network, and we just see that as you use better and better neural networks, you just get much better outlier detection, and it greatly exceeds all of the previous literature that was, say, looking at pixels, coming up with statistical generative models and things like that. So one algorithm I'm going to dive into in particular here, because it's near and dear to our hearts, is this idea of how can you automatically detect mislabeled data in a data set. And this is an algorithm we developed on our team called confident learning. And it's really a framework for finding label errors mainly in classification data and being able to measure the likelihood of each data point being mislabeled so you can prioritize which data do you want to review, like the most when you have a limited data review budget, as well as understanding at a more global scale overall in the data set, like how often is each class being mislabeled or which classes are the hardest ones, things like that. And really the key idea here is that we want to use a model's predicted class probabilities to find the label errors. So it's really simple. This allows it to work with any machine learning model because we are not dictating how you produce these predicted class probabilities, right? You're probably all familiar that any machine learning model can produce these. And essentially at its core, what we're doing here is deciding when to trust the model over the data. And this decision takes into account the confidence of the machine learning model, how likely it is to predict each class, as well as how good the model is when it is this confident in its predictions. So essentially, when we see that the model is very confident, we've seen that it is very good at predicting data like this when it's this confident. But here in this case, it's making a totally different prediction than the annotated label. That's when we say this data point is probably mislabeled. And just to give you a sense of how messy some data sets can be, again, these are like really nice data sets, relatively speaking, because they've been curated by many, many machine learning researchers and studied by many papers. But data sets can have all kinds of annotation issues. One, of course, is just hard or ambiguous examples, as I mentioned. You can have examples that are just out of distribution or outliers that really don't belong to any of your classes. You can have maybe you framed your data annotation task incorrectly, and actually you said this was a multi-class classification task. Actually, these all are framed as multi-class classification in machine learning research, but often many of these data sets contain data which should have been multi-labeled because more than one of the classes applies. And then you just have straight up errors that were just made by human accidents where, like these are totally correctable. If you had more annotators go look at this data, they would probably see it immediately. And these are the easiest to deal with. And really confident learning helps you deal with all of those. The basic idea here with confident learning to improve a machine learning model is you can just run this method to estimate which data points are mislabeled and then just delete all of those data points from your data set and then just retrain your original machine learning model. And so it's a really, really simple approach, but surprisingly it outperforms like a lot of these. So there's a big field of research on machine learning with noisy labels where these are model-centric methods where they actually go and try and adjust your loss function, use certain kinds of regularizers and things like that to accommodate the noisy labels. But we find that this really simple data-centric approach of just deleting the data estimated to be bad just works a lot better. And really a big reason for that is because when you have errors in your data, these model-centric methods that try and deal with it in a more smooth manner, by adjusting the loss for certain data points, they're still like propagating these errors through. Maybe they're downweighting them a bit, but they're still there. And that just really has much less benefit for improving machine learning models. To give you a more popular example nowadays, like a lot of folks are fine-tuning LLMs, say for text classification, especially in customer service applications like banks, big companies. The first step is always to classify the intent of the customer. And often this is like the closest thing they have to LLM and generative AI deployment today in many of these big companies because they're much more willing to deploy this than something open-ended that's going to give you back arbitrary text. So here we might consider classifying just the politeness in some text from some online forums, and we can run our confident learning algorithm from our Cleanlab library. And it will detect issues like this, where this text example is labeled as impolite, but it doesn't really seem impolite at all. And then what we can do is we can fine-tune 3 different LLM models and just zooming in on one. So these are like the most popular LLMs that you can fine-tune via the OpenAI API. And let's just zoom in on the Da Vinci model here. So in black, what we're showing is this model fine-tuned on the original raw data set. In yellow, we're showing this confident learning approach of just deleting all of the data automatically that was automatically flagged as being mislabeled. And then in blue, we're showing actually going in and having humans review some of that data. So just the subset of data that was flagged as being likely mislabeled and correcting some of the labels where appropriate. And you can see, so in all three of these bars with the DaVinci LLM, it's the exact same OpenAI code that's being called. There's no actual change in any of the machine learning. And you can just see how the model performance can go up drastically as a result of this data correction and of even just data filtering, right? This is like a trivial operation, basically, to do, and doesn't really involve much human labor at all. Getting the blue performance does involve human labor, but it's much, much less than you would have needed to do, just going through the data set yourself and trying to figure out how you can improve it. All of this works for arbitrary data sets, as I mentioned. So here is just another anecdote of the same thing, but just with XGBoost on a tabular data set. And again, you're just seeing that auto-filtering a lot of these detected label issues gives you a big boost in performance without any change in the model, but then actually going and fixing this subset of the data that has been identified as particularly relevant really gives you much bigger gains, even more. All of this will work for pretty much any kind of human annotated data set. So RLHF data is really popular nowadays. Again, super dependent on human labor, human annotation. Humans just make mistakes all the time. So in RLHF data, like human annotator is supposed to choose which completions from an LLM are more appropriate for a given prompt. And here you see that the human chose the blue completion over the gray one, but actually the blue completion is pretty inappropriate for this prompt, and it's just a standard error, in an RLHF data set, and there's countless of these, and they actually really, really affect the performance when you're trying to do the reinforcement learning with these really noisy signals. Also for just prompt evaluation, or more generally, model evaluation. So what I showed before was, correcting the training data for getting good machine learning models. But even when we're just trying to evaluate, say, prompts or hyperparameters or some aspect of our models to make the decision whether to deploy them or not, here what we're looking at is two prompts within the same category. So maybe two chain of thought prompts, two few shot prompts. And what we saw was really that on an observed data set, this was a sentiment analysis data set that was really noisily labeled using Mechanical Turk. We saw that basically the observed accuracy according to the given annotations in the original data set showed that this first prompt was always the better one. But then when we actually went and cleaned that data set up, we found that actually the second prompt was often the better one. And this is just showing, like you can be making really suboptimal evaluation decisions when your data are noisy. And even more extreme is when you're doing things like few shot prompting, the quality of the data that you're feeding in and the categorizations or class annotations really, really matter, as you might expect. So one thing that's natural, if you know that you're in such a setting where you have human annotators making all kinds of mistakes, is to utilize multiple annotators. This is standard stuff. And so when you're dealing with such data, the main questions that come up are really like, what is the best consensus label that we want to apply for a particular input? How confident are we that this label is actually correct, right? Or should we go have more annotators look at this? And then which of the annotators is not doing such a good job? And so this is just summarizing that. And really, in the statistical world and data mining, machine learning literature, there's like thousands of algorithms on pretty complicated probabilistic models to answer those questions I just showed. But again, we can think about how can we just reinvent this space just using machine learning model outputs, which already know a lot about the data. Especially you can imagine in certain scenarios, you have like one data point that's only been labeled by a single annotator, and a lot of the traditional statistical approaches just can't really do anything with that information because that data point was only labeled by one annotator. All you can basically do is estimate how good that annotator is on average and apply that trustworthy level to that data point. But a machine learning model can actually generalize across data points if it's seen ones with similar features and have a much better perspective on how good this annotator is doing in this one data point. And so our idea here is really just what is like the best approach to get the best probabilistic machine learning. It's on model ensembling, right? For all of you who have competed in Kaggle, that's the thing that always wins, is just combining a bunch of models. That gives you really, really good probabilities too. And so what we can do here is treat each annotator just as if they are another machine learning model and form a simple weighted ensemble with actually a trained classifier and human annotators, treating each of them as a machine learning model, and apply what are almost essentially standard machine learning ensembling techniques to form a weighted ensemble of these aspects. And the weights here will naturally give you a sense of, how trustworthy each annotator is relative to this trained machine learning model. And this method, which we call Crowdlab, will then properly account for, how many annotations did one example receive. Because if you had an example with like 100 annotations, say, then you probably don't really need to consider the machine learning model's prediction. It's kind of irrelevant at that point. But as I mentioned, if you have an example with just one annotation, the machine learning model probably will help you better understand a lot how trustworthy that annotation is. And of course, it's important to also account for, how good this machine learning model is in the first place, because we want all of this to just work with arbitrary machine learning systems where we have no insight in how they were trained or, like what architecture they're utilizing. And so here you can see just forming, here we're measuring how accurate are the resulting consensus labels. So here, based on the ensemble, if I go back, we can get like a probabilistic estimate of each possible class for each model, for each data point coming from this ensemble. And then we can just use as consensus label the most likely label from that ensemble. And we can see here, so here we're measuring the accuracy of these consensus labels on a data set. It's a variant of the famous CFAR10 data set where we know the ground truth labels for each example, as well as we have each image being annotated by between 1 to 10 annotators. And we can see that compared to all these traditional statistical techniques like Dowd-Skeen and this GLAD method and the simple majority vote, doing this Crowdlab approach just gives you much more accurate consensus labels overall. And also, if we sort our data by these quality scores, which measure our confidence that the current consensus label is correct. So if we sort by all of these, what we really care about is that the data points with the lowest scores are the ones whose consensus labels are most often wrong. And so we can measure, this is essentially like an information retrieval task of retrieving the most incorrect consensus labels in the current data set, which we can measure via area under precision recall curve. And again, we can see that using this Crowdlab method just outperforms all of these more traditional probabilistic generative models that have been really dominating this area for a long time. And all of this, I should mention, we're doing it with 2 different machine learning models that are pretty different, like a Swin transformer and a really small residual network. And you can just see, how these findings generalize across machine learning models. And finally, we can measure how good each annotator is. Again, because we have ground truth labels here in this data set, we can actually truly know how good each annotator is. And we can just measure the correlation between the estimated annotator scores and the ground truth of how good they really are. And again, just see that these estimates are much higher for approaches like this Crowdlab approach that leverage a machine learning model. A really simple extension of what I just outlined is to this active learning problem where you are trying to decide which data is going to be most informative to label. And something that really isn't considered in most active learning literature is that the active learning or the annotation will just be imperfect, right? Almost always. And often it's actually better to go re-annotate a data point that was previously mislabeled than it is to go collect annotation for a new data point. You can think about it like having a teacher who is sometimes lying to you, like every 100 statements they make, one of them is a lie, and that's just much more damaging than them teaching you a lot more new facts. And so, yeah, going back to that Crowdlab method where we have those scores of how confident we are that the current consensus label is correct, we can just literally use those scores to decide which data should be re-annotated, as well as taking the classifier's traditional uncertainty estimates to decide which unlabeled data we want to go collect the first annotation for. And we have a way of trading off between these 2 options. And you can see that when you're doing this, you're just getting much better performance at a given data labeling budget than traditional active learning methods, which may not be willing to go re-annotate data and are only relying on machine learning model confidence estimates. So really, this re-annotation process is really helping here. And to give you some case studies of where this kind of thing is being used in the real world, one of the biggest banks in the world, BBVA, they published this blog that you can go read, where they're trying to train a machine learning model for categorizing financial transactions in their online banking app. And they're using this active lab, active learning framework I just talked about. And essentially, the outcomes here are that they're able to train the same model they previously used in the older version of their application, but they're now able to label 98% less transactions with human labor, and they're able to improve that machine learning model by 30%, and this is all without any change in any of the ML pipelines. At Google, they use a lot of the previous work I talked about on confident learning to detect label errors for finding and fixing label errors across the speech samples in their voice assistant products, and this is done at Amazon and many of the other biggest tech companies that have voice assistants. And then many consulting firms have found new applications of this technology, way outside the machine learning space that we never really envisioned, like Berkeley Research Group, where they discovered, this is super useful for law firms which are trying to decide what evidence is relevant or not to a court case, and actually submitting, this is called e-discovery, submitting that set of evidence as the permissible set that will be allowed in the court case. They have lawyers doing this annotation and data review and paralegals, and it's really expensive. And algorithms like confident learning can be really useful here for really reducing the amount of labor required to generate a good curated set of evidence to submit. And I want to emphasize that everything that I talked about here, we published all of this in research that you can go check out. The Cleanlab library is totally free to use and fully open source. And I just really want you to think about, what we feel like the big gap today is that you just have a lot of tools for storing your data and manipulating it and getting it into the right place, but you typically just have lower quality data than you want, and that's due to the information in the data itself. I mean, there used to be a lot of problems with broken pipelines, but we think, traditional data quality and ETL tools have, really mitigated a lot of those. And the remaining issues in data really are at the information level, which we think you need machine learning to help you discover. And really to go from that to successfully using one of the many, many model deployment, model training solutions that exist today, we think the gap here really is that you need these types of data-centric AI software and algorithms that can help you, take raw data, use your initial AI or machine learning model to figure out how to correct this data at the informational level to produce better versions that then give you better deployed machine learning models. And one final thing I'll touch on is just how we're doing this behind the scenes is we're always, really carefully considering the confidence of machine learning models. Essentially, we're trying to trust the machine learning model over the data or weigh its confidence against multiple human decisions related to the data. And so like with LLMs, it's really popular nowadays. We can apply everything I was just talking about to discover problems in sequence-to-sequence data sets where you just often have bad human-generated outputs, bad summaries, bad things like that. And the way we're doing that is we developed a trustworthy language model that can give confidence scores for any possible output that you might want from the LLM. That's all I have. Thank you so much for being here.
We may just take one question. Anyone has any questions? Just one.
So you're pruning noisy data by counting the probabilistic threshold to estimate noise? Is that what you're doing?
Mm-hmm. Yep.
All right.
That was exactly it.
Fantastic. Thank you so much. Sorry, we're running short on time. So if you have any other questions, please feel free to post on the app. You can address those questions, right? Awesome. Thank you so much.